All right, so last support class, a couple of weeks ago, we were talking about the algebra and the arithmetic of the complex numbers, the meaning behind the number I, the complex constant I, and complex numbers of the form a plus bi. The algebra and arithmetic we did last time is central to what we're doing here, but we're actually looking at the complex numbers from a different perspective, and this is where the trigonometry is going to come in the parent class. So the complex numbers have a unique geometry to them. To sort of motivate this, think about the real numbers for a moment. The real numbers are often placed on what we call the number line, or the real line is another word for that. This is the number line. We're all familiar with this. This number line contains all of the real numbers. Even though I've only labeled the integers, I can find, for example, 0.5. It would be right here. Or pi would be over here somewhere. All of the real numbers, whether rational or irrational, are on this number line. But they also completely fill up that number line, which means there's no space on that line for complex numbers. If I'm trying to figure out a way to visually represent a complex number, where do I put numbers like I, for example? Well, those numbers are off the line. I would live up there somewhere. So how do we make sense of this if we want to visually represent all complex numbers? The trick is to take a complex number of the form a plus bi and associate it with the ordered pair a, b, which means we can plot these things like points in two-dimensional space. Now, the way that I've written this, a is the real part of this complex number, and the value of a turns into what looks like an x-coordinate for an ordered pair. So that means that the x-axis on this coordinate plane here is going to represent the real parts of a complex number. Similarly, the b is the imaginary part of this complex number. It becomes what we would think of as the y-coordinate, which means the y-axis is what we call the imaginary axis. So this is a way that we can graphically represent complex numbers. To give you an example, if I wanted to figure out where 3 plus 2i lives in the complex plane, which is what we call this, I would associate that with the ordered pair 3, 2. And then I would find that ordered pair in the plane. 3, 2 would be right here. And that's going to be the point 3 plus 2i. Okay, and I can do this with really anything. For example, if I wanted to plot the point, even just like, say, negative 2i. Well, the real part of this complex number is 0, because I could put a 0 in front of this. So I would think of that as 0, negative 2. 0, negative 2 would be right here, and so this is going to represent the point negative 2i. Similarly, if I wanted to plot, say, a real number, say the number 4, well, now I can think of this as 4 plus 0i, which would be associated with the point 4, 0. That would be right here. That's like the number 4. So real numbers live on this axis. Purely imaginary numbers, meaning imaginary or complex numbers whose real part is 0, those would live on this vertical axis. And complex numbers that are neither purely real nor purely imaginary are going to be in one of the quadrants, just like this. Let's do one more. So if I wanted to plot, for example, 1 minus I, the real part is 1. The imaginary part is negative 1. It's the coefficient on that I. So this would be associated with the point 1, negative 1, which is down here. This would be the point 1 minus I plotted in the complex plane. Okay, so the first thing that you're going to be doing, I'm going to pull this up. First thing you're going to be doing in the assignment is just plotting these complex numbers the way that we're doing here. And then you're going to do a little bit more. You're going to kind of mix some of the arithmetic that we talked about last time with this idea of the geometry of the complex number. So for example, if I say that W equals, let's say, 1 plus I, and z equals 2 minus 3i, you may be asked to plot w plus z and w times z. We know that if we add or multiply two complex numbers, the result is another complex number, and that's something that could also be plotted in the complex plane. So if I were to add these two, for example, 1 plus 2, that's 3. I plus negative 3i would be negative 2i. I would associate this with the point 3, negative 2. That would be here. So this is like the point that I got from doing w plus z. Or if I wanted to multiply w times z, 1 plus I times 2 minus 3i. Again, we treat it like FOIL, so I'm going to get 2 minus 3i plus 2i, and then minus 3i squared. This would equal, so I know negative 3 times I squared is negative 3 times negative 1, or just 3 plus 2, that would be 5. Negative 3i plus positive 2i would be minus I. So I would associate that with the point 5, negative 1. 5, negative 1. So WZ is right there. In the parent class, we're gonna talk about some geometry associated with the addition and multiplication, as well as subtraction and division of complex numbers. Basically, if I were to look at the points w and z, in this case 1 plus I and 2 minus 3i, and plot those 2 points in the coordinate plane, the sum and the product of those two points, when plotted the way that we did here, have a special relationship to where the original points exist. But that's what we're going to talk about in the parent class. We're not going to worry about that here. Okay. Only a couple more things to talk about. So, okay. Associated with the points that we're plotting in the complex plane are a couple of values of interest, and it's the same basic idea behind what we did with polar coordinates. So suppose I plot some point, I'm going to call it A plus B I. If I were to plot this point in the plane, in fact, I'm going to change what I'm calling that. Let me do this right here. I'm going to call it X plus I, or yi, just so it's a little more clear that I'm thinking of this point right here as having an x and a y coordinate that correspond to the real and imaginary parts of this complex number. If I were to take that point and measure its distance, and I'm actually going to call this complex number z to give it a simpler name. The distance from the origin to this point in polar coordinates, we were calling that distance r. Still talking about that same distance, but I'm going to call that by this symbol. This is called the magnitude of z. Notice it looks like an absolute value symbol, and sometimes we also do call this the absolute value, but more commonly it's called the magnitude of z. In addition, we want to talk about the angle that z creates with the positive x-axis, or the positive real axis, which is what we call it in the complex plane. In polar coordinates, I would be calling that theta, and we're oftentimes still going to be using theta here, but another term for that is the argument of z, which we write that way, capital A, then Rg of z, like this. Both of these quantities we find the same way that we do with polar coordinates, because it's basically the same idea. So the magnitude of z is equal to the square root of x squared plus y squared, and the argument of z, if we call that theta, then we have this relationship. Tangent of theta equals y over x. Okay, so I want to do an example or two where we're finding both the magnitude and the argument of a complex number. All right, so I'm going to say let z equal, let's say, 2 plus 5i. I want to find the magnitude of z and the argument of z. Okay, so the magnitude of z basically just using a formula. It's the square root of the real part squared, 2 squared, plus the imaginary part squared, 5 squared. Notice I'm not putting the I in here. The I doesn't belong here. It's just the coefficients, 2 and 5. That's going to be 4 plus 25, which is 29. I get root 29 for that. Now, how about the argument? Well, again, the argument we oftentimes call theta. So either of these terms apply here, or symbols, I should say. So that means the tangent of theta is equal to y over x, 5 over 2. Okay? Now, this is not a familiar value for tangent, but there is a solution to this. I'm just going to represent my answer in terms of an inverse tangent. I do need to be careful, though, because remember, inverse tangent only gives us solutions in the first or fourth quadrants. So if this complex number, if I were to plot it in the complex plane, is somewhere other than the first or fourth quadrant, I'd have to adjust somehow. But fortunately, that's not the issue in this case. So if I were to plot this point, notice both my real and imaginary parts are positive. That means this would be in the first quadrant. So this is in quadrant 1, which means my argument of z, which is the same thing as theta, is equal to the inverse tangent of 5/2. And yeah, I could plug that into a calculator, but I'm satisfied just leaving it in this form. So this answers both of those questions. Okay. I could, let's take a look at another example. Let z equal, I'm going to say negative 3 minus 3i. Okay. And I want to do the same thing. Find the magnitude of z and the argument of z, which we're calling theta. Okay, so again, magnitude, same idea. Magnitude of z would equal the square root of the sum of the squares of the real and imaginary parts, negative 3 squared plus negative 3 squared. Okay, this would be 9 plus 9, or 18, which simplifies to 3 root 2. That's the magnitude of this complex number. The argument, again, we find using this relationship. Tangent of theta equals y over x, or negative 3 over negative 3. That equals 1. Now, the value that I'm getting here is a familiar value for tangent. If I were to take the inverse tangent of this, I'd get pi over 4. But that's a problem, because pi over 4 is in the first quadrant, and if I go back here and I look at this complex number, I can see that it belongs to the third quadrant. Both x and y, or the real and imaginary parts, are negative here. So that being the case, pi over 4 is not correct. We've seen that if we're in the wrong quadrant when taking an inverse tangent like this, you can add pi to your answer. So this would be equal to pi plus pi over 4, which is 5 pi over 4. And that gives me my magnitude and my argument. That's essentially all you need in order to do the assignment. You're going to have a couple of problems at the end where you do something similar to what we did on this page. I give you 2 complex numbers, and you're working with the sum or the product of those complex numbers. In particular, you're actually working with the product. The idea there is I'll give you 2 complex numbers, and you find the magnitude and argument of both of those, and then you look at the magnitude and argument of a third complex number that you would get from multiplying the 2 that I gave you. And there's a relationship between all of those quantities that I'm not telling you right away. I just want you to think about and see if you can determine what that connection is. But that's something that we're going to explore in more depth in the parent class. Okay, so that's going to be it for this one.